guys, so today we're going to be going over the homework. I have over here on the board nicotine, which is in your homework, and they're asking us what is the molar mass. So the very first thing that we have to determine is going to be the chemical formula, because we need the chemical formula to figure out the chemical mass. But we're given this skeletal structure, so in order to find the chemical formula, we're going to have to get it from the skeletal structure that's provided to us. Before you get started, know that every time that two lines are connecting, you're going to have a carbon. At the end of a line, you're going to have a carbon. After you determine how many carbons there are, know that each carbon has to have 4 bonds. So with that said, let's go ahead and get started. Let's start over here, right? 2 lines are meeting, we're going to have a carbon. 2 lines are meeting, we're going to have a carbon. 2 lines meet, carbon, carbon. There's a nitrogen there, so no. The end of a line, there's a carbon. Lines meeting, carbon, 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 and carbon. After you do that, you have to go to each carbon and make sure that it has 4 bonds. If it does not have 4 bonds, you have to add hydrogens up until it reaches 4 bonds. So first off, over here, we have carbon and there's just 1 bond. So you know that it needs to have 4 and it has 1, so you're missing 3, right? 3 bonds. And for every bond that we're adding, we're going to be adding a hydrogen. So we're missing 3. So here's 1, 2, 3. Next, this carbon over here. Right now, it has 2 bonds. It should have 4. So I'm missing 2. So I'm going to add 1 hydrogen and another hydrogen. Over here, 2 as well. So I need 2. Same thing here, right? I have 2 bonds. So I'm missing 2 bonds. Over here, you have 1, 2, 3, 4. We don't have to do anything. Over here, you have 1, 2, 3, 4. We don't have to do anything there. These lines, right, they are double bonds. So over here, we have 4. We leave it alone. Over here, 1, 2, 3. We need 4, so I'm missing 1. I'm going to add 1 hydrogen. Over here, 3, I need 1. Over here we have 3, I need 1 more. Over here, 1, 2, 3, I need 1 more. And we are done. Anything that is not carbon, you're going to leave it alone. You're not going to be adding any hydrogens to anything other than carbon. After you do this, you've done the hard part. Do not mess up when you're counting each carbon and each hydrogen and any other element present for the chemical formula. So first off, I know that I have carbon. Let me write that over here. So I have carbon, I have hydrogen, and I have nitrogen. Nothing else. Alright, so first you write carbon, then you write hydrogen, and then in alphabetical order. So we're going to go ahead and count our carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, let me use another color. For hydrogen, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. For nitrogen, I have 1 and 2. And now that you've determined the chemical formula, we can go ahead and figure out the molar mass. So here we have nicotine again, and now they're asking us, is this soluble with water? So first, before answering, let's go ahead and review the solubility rules. If we have something polar, mix it with something polar, it's going to be soluble. If we have something non-polar, mixing with something non-polar is going to be soluble. If we have something ionic, mixing with something polar, is going to be soluble. Anything other than that is not. So first of all, water is polar. Let's go ahead and look over here at nicotine. We have a polar group over here, we have a polar group over here, but if we look at the rest of the molecule, we have a lot of non-polar groups. So the ratio of polar versus non-polar, right? There's more non-polar, and therefore we can go ahead and determine that it is not very soluble. Before we move on to the next question, let me introduce you to this chart right here. If we're going from grams to moles, you have to use the molar mass. The mole ratio you're going to have to use every time that we're going from one compound to another compound. Then for moles, you can go ahead and go to grams, same thing, using the molar mass. Or for moles, you can go to molecules. And if you're going from moles to molecules, you're going to use the Avogadro's number. And here it is with the units. And then for molecules, you can go ahead and go to atoms. So with that said, let's go ahead and do the question. So the question is asking us, how many grams there are in 0.74 moles of aluminum sulfate? So we are right here, and we'd have to go right here, and therefore use the molar mass. So let's go ahead and get started by writing our starting point. 0.74 moles of aluminum sulfate. We need the molar mass, so the molar mass is going to be 342.15 grams over mole. And this is the same thing as 342.15 grams over mole. I like to use this version better so that it's easy for me to see when the units get crossed out. So over here, I want grams. So grams is going to go on the top. And I'm trying to get rid of moles, so that's going to go on the bottom. Whatever I want always goes on the top. What I want to get crossed out goes at the bottom. So looking over here at the molar mass, the units are correct, right? Grams over mole, grams over mole. So since they're already in the way that they have to be, I don't have to take this fraction and flip it. I can just leave it as it is. So I'm going to take that number and write it over here. That's going to cross out my moles, and I'm going to end up with grams. So the final answer is going to be 253.191 grams. Now let's go ahead and look at the significant figures. So we have two sig figs here, and therefore our answer should also have two significant figures. Therefore, my final answer is going to be 250 grams. The next question says, the mass of 1.63 times 10 to the 21 silicon atoms is, so we're going from atoms all the way to grams. So let's get started with what we are given, which is 1.63 times 10 to the 21 silicon atoms. Looking over here at our chart, the next step is molecules. So again, what we want goes on the top. I want molecules, and I want to get rid of atoms. So that's going to be going at the bottom. So there's just one silicon atom, and that one silicon atom is also just one molecule. So 1:1. 1-to-1 ratio, so the number does not change, but you can see how atoms get crossed out. So now we have 1.63 times 10 to the 21st, but we have molecules. So let's carry this over there. We have molecules, so we're right here, and we're trying to go from molecules to moles. So I have to use the Avogadro's number. Let's go ahead and do that. Times. Again, what I want to get rid of goes at the bottom. So molecules go at the bottom. And what I want, which is moles, is going to go at the top. If you look over here at the Avogadro's number units, we have 6.022 times 10 to the 23rd molecules over moles. If you look over here, what we need is moles over molecules, which means that you're going to have to take this fraction and flip it, okay? So the 6.022 times 10 to the 23rd is going to go down here. 6.022 times 10 to the 23rd. Okay. This is going to equal to 0.002707. And notice how my molecules are crossed out. So now I have moles. Okay? So let me carry that number over there. So I wrote our mole answer over here. At this point, we're right here. And our goal was to get mass, so grams, right? So we're in moles, we're trying to go to grams. We have to use the molar mass. So again, let's go and do that. First off, I want grams, that's going to go at the top. I want to get rid of moles, so that's going to go at the bottom. And over here, I'm going to be writing the molar mass, which is 28.09. So that's going to get rid of my moles. And now I end up with grams, which is what we wanted. And the final answer is 0.076032 grams. Now let's look at significant figures. We started with 1, 2, 3 sig figs. So our final answer should also have 3 significant figures. So we have 1, 2, 3. Stop right here. We don't have to round. So the final answer is 0.0760. Or you can go ahead and write it in scientific notation, which is the same as we're moving it 1 twice to the right, which means it's a negative exponent. So that would be 7.60 times 10 to the negative 2. So here is my answer. The next question is asking us to figure out the molar mass of Tylenol, which I have over here. Like I mentioned before, if you need to find the molar mass, we need the chemical formula. We have this skeletal structure over here, so we can use this to figure out what the chemical formula is. A reminder, every time that we have lines meeting, there's a carbon. At the end of a line, there's a carbon. Each carbon needs to have 4 bonds. If it does not have 4 bonds, you need to add hydrogens up until it does. So let's go ahead and get started. The end of a line, so we have a carbon. Lines meeting, we have a carbon. Here is nitrogen, we leave that alone. Lines are meeting, we have carbon. Lines are meeting, carbon. Lines meeting, carbon. Lines meeting, carbon. Lines meeting, carbon. There's an oxygen there, we leave that alone. Lines meeting, carbon. After we figure out the carbons, we're going to make sure that each of them has 4 bonds. So over here we have 1, we need 4, so I'm missing 3, and therefore I'm going to be drawing or writing 3 hydrogens. Over here we have 1, 2, 3, 4. We leave that alone. Over here we have 1, 2, 3, 4. We leave that alone. Over here, 1, 2, 3. You're missing 1, so I'm gonna write 1 hydrogen. Over here, 1, 2, 3. You're missing 1. Same thing. I'm going to draw 1 hydrogen. Over here, 1, 2, 3, 4. We leave that alone. 1, 2, 3. We need 1 more, so write 1 hydrogen. 1, 2, 3, 4. 1, 2, 3, 4. We already did that one. After you've done this, you've done the hardest part. So don't mess up by counting how many there are of each atom. So over here, we have carbon, and we said first we write carbon, then we write hydrogen, and then in alphabetical order. So then it will be nitrogen and then oxygen. Now let's go ahead and figure out how many of each. So for carbon, we have 1, 2, 3, 4, 5, 6, 7, 8. For hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9. For nitrogen, just 1. So we don't have to write a 1 if it's just 1. For oxygen, we have 1 and 2. So we write that down. After you figure out the chemical formula, then you can use the periodic table to figure out the molar mass. So your final answer is going to be 151.16 grams over mole. That's our answer. The next question is asking, a tablet contains 325 milligrams of Tylenol. How many moles is that? So first off, our starting point is 325 milligrams, but looking over here, we always get started with grams, right? So now we know that the very first thing that we will have to do is change this to grams. So if we do that, that becomes 0.325 grams. All right, now that we have grams, then they're asking us to go to moles. So we're here, we have to go to moles, therefore we have to use the molar mass. So let's do that. What I want is going to go at the top. What I want to get rid of is going to go at the bottom. And the molar mass that we found earlier was 151.16. This is going to be able to cross out grams, and you end up with moles. And the final answer would be 0.00215. Make sure that you have the correct number of significant figures. We have 3. We end up with 3. That's good. Alternatively, you can go ahead and write it in scientific notation. So we will move 1, 2, 3 times to the right. So that is a negative exponent. That will be 2.15 times 10 to the negative 3. And that will be the final answer. The next question is asking us, how many molecules are there in 325 milligrams of Tylenol? First of all, we already got the moles, so I went ahead and I wrote that. But we will have to get started in moles, and then they're asking us to go to molecules. So we're going from moles to molecules. I have to use the Avogadro's number. So let's do that. Times. I want molecules. What I want is going to go at the top of the fraction. Molecules. What I want to get rid of is going to go at the bottom. Might have written this too big. So looking over here at the Avogadro's number, we have moles over molecules, so there's no need for me to flip this fraction. I can just go ahead and write it here. 6.022 times 10 to 23rd. Now you're going to go ahead and plug this into your calculator, and the answer is going to be 1.29 times 10 to the 21st, and then we have molecules. We check the significant figures, so we had 3 starting up, we have 3, we're good. The next question is asking, how many carbon atoms there are in 325 milligrams of Tylenol? And I've written over here the chemical formula that we found out at the beginning of the question, and over here we have the amount of molecules that we found in the previous question. So now they're asking us to go from here, from molecules to atoms. So let's go ahead and do that. We want carbon atoms, so whatever I want is going to go at the top, carbon atoms, and I want to get rid of molecules, so that's going to have to go at the bottom. Okay? And now we have to find out what number am I gonna go ahead and put in here. So we have 8 carbons. So that's the number that's going to go there. And there are 8 carbons in this one molecule. So 1 molecule. You're gonna go ahead and plug this into your calculator, and your final answer is going to be 1.0358 times 10 to the 22. Now we're going to go ahead and look at significant figures. We have 3, we have to have 3, so I'm stopping right here. Looking at this number, I'm going to have to round up. So my final answer is 1.04 times 10 to the 22. The next question is asking, how many total atoms are there in 325 milligrams of tanninol? Again, this is the chemical formula for it. We've already figured that out. And then I have over here the molecules that we've already found out. So once again, we're going from molecules to atoms. Let's do it. Atoms go on the top because it's what I want. I want to get rid of molecules. So that's going to go at the bottom. We just have 1 molecule. So there goes a 1. And they're asking how many total atoms. So how many total atoms are there in this 1 molecule? We have 8 plus 9 plus 1 plus 2. That's a total of 20 atoms. Now you're going to take these numbers and using your calculator, you're going to multiply. And your final answer is going to be 2.58 times 10 to the 22nd. And let's go ahead and check significant figures. We have 3. We also have 3. We're good. Now we're going to be balancing some reactions. If you see anything like this in the test, just be happy, right? We've done this so many times, and this is your opportunity to get many points. So what we're going to do first is go ahead and write each element on each side of the reaction in a symmetrical way so that it's easier for me to keep track. Alright, so on the reactant side, I have 2 nitrogens, and on the product side, I just have 1. On the reactant side, I have 2 hydrogens, and on the product side, I have 3. So we have 2 versus 1. You ask yourself, 1 times what is going to equal 2? The answer is 2, right? So I'm going to put 2 right here. Now this becomes 2, but this hydrogen is changed now, right? We have 3 initially, but by putting this coefficient here, we now have 2 times 3, which is going to equal 6. Now you have 2 hydrogens on the reactant side versus 6 on the product side. So you ask yourself, 2 times what is going to equal 6? The answer is 3. So I'm going to put 3 over here, and now this is 6. And you have 2, 2, 6, 6. That one's balanced. So I went ahead and I wrote each element down on each side of the chemical equation so that it's easier for us to keep track. Now let's see how many there are of each. So for potassium on the reactant side, just 1. On the product side, just 1. Chlorine on the reactant side, we have 1. On the product side, we have 1. Oxygen in the reactant side, we have 3. In the product side, we have 2. So what we're seeing here that is different is the oxygens. So we have 3 versus 2. We have to find a common denominator. So that's going to be 6. Then you ask yourself, 3 times what is going to equal 6? The answer is 2. So I'm going to take 2 and put it in here. Now this becomes 6. But because we put this coefficient in front of this whole compound, now this potassium is affected and this chlorine is affected as well. So we had 1 initially, but I put the 2 here. So now we have 2 times 1, which is 2. We had 1 chlorine, but I put the 2, so same situation. Now we have 2. Over here, we said that the common denominator was 6. So you ask yourself, 2 times what is going to equal 6? The answer is going to be 3. So I'm going to take 3 and put it over there. And now we have 6 here. But now we have 2 versus 1 and 2 versus 1. So let's fix that. You ask yourself, 1 times what is going to equal 2? The answer is 2. So I put a 2 here. Now this becomes 2. And because I put a coefficient in front of CL, this becomes 2 as well. So to check, we have 2, 2, 2, 2, 6, 6, and we're good. We have done a lot of these problems, so what I did is just giving you the final answer here so that you can go ahead and double check your answers. Feel free to pause the video so that you have more time to verify. Next, we're going to go ahead and figure out the chemical formulas for each of these reactants. Then we're going to figure out the chemical formulas for the product. Then we're going to go ahead and we're going to balance it. And after that, we're going to go ahead and determine the physical states using the solubility rules. So let's go ahead and get started. We have barium. And we have nitrate. Nitrate was a polyatomic ion that you were supposed to memorize. Barium is in the second group and therefore has a 2+ charge. After you go ahead and determine what the charges are, you're going to go ahead and take the charge and go down and across. Take the charge and go down and across. Okay. And your final is going to be this. I put the parentheses because we have a polyatomic ion, so it's important that you put the parentheses and then the number after. Then let's go ahead and do the same thing with this one. We have ammonium phosphate. So for ammonium, we have NH4 plus 1, and phosphate we have PO4 in the charge -3. So then, let me use another color. You're going to take the charge of each and you're going to go down and across, and your final answer is going to be NH4. Notice how we have a polyatomic ion here, so I need to use the parentheses and have that 3 go down here. Now we have phosphate, and it's just a 1, so there's no need for me to write it down. Therefore, no parentheses are needed. So here we have our reactants. So I just went ahead and rewrote it so that we have more space. Now let's go ahead and figure out what the products are. So first of all, I'm going to go ahead and write the positive of one reactant next to the negative of the other reactant. So the cation of one reactant next to the anion of the second reactant. So let's go ahead and do that. We have barium 2+, right? And PO4 3 negative. Let me go ahead and put this. I took this one and I took this one. All that I did was write them next to each other. Right, this is very ugly. Okay, so now that I did this, I'm going to go ahead and take each of these charges and I'm going to go down and across and down and across. My final answer for this product is going to be this. 3. You have to write the parentheses around the phosphate because it's a polyatomic ion. And we have a 2 down here. So that's for the first product. For the second product, we're going to be doing the exact same thing. We're going to take the cation of one, right here, and write it next to the anion of the other. So let's go ahead and do that. I have NH4 plus next to NO3 negative. I'm going to take these charges and I'm going to go down and across, but they're both 1 anyway, so it doesn't really matter because they're not written. 4, and O3. And there we have the second product. Then you're going to be using the solubility rules to figure out which one is aqueous and which one is solid. If it is soluble, you're going to write AQ. If it is insoluble, you're going to write an S for solid. That means that a precipitate is formed. So this is going to be aqueous, this is going to be aqueous, this is going to be solid, and this is going to be aqueous. Now let's go ahead and balance it. I went ahead and I wrote everything out. I kept all of the polyatomic together in both the reactant side and the product side, because if you're looking over here, this polyatomic ion remains together on the product side. So there's no reason for me to split them up. So let's go ahead and see how many of each we have. For barium, just 1 on the reactant side. On the product side, we have 3. For nitrate, on the reactant side, we have 2. On the product side, we have 1. For ammonium, on the reactant side, we have 3, right? And on the product side, just 1. For phosphate, in the reactant side, we just have 1. And on the product side, we have 2. So let's go ahead and balance this. We have 1 versus 3, so you ask yourself, 1 times what equals 3? The answer is 3, right? So I'm going to go ahead and add a 3 right here. This now, this becomes a 3. But because I have this coefficient here, now this nitrate is impacted as well. I had 2 initially, but because I put that 3 there, now I have 3 times 2, which equals 6. Okay, now we have 1 over here versus 6 over there. You ask yourself, 1 times what is going to equal 6? The answer is 6. So I'm going to go ahead and write that down. 6 over here. Now this becomes 6, but because this coefficient is now in front of ammonium, this is impacted as well. I had 1 initially, right? So now you have 6 times 1, which equals to 6. On the reactant side, I only have 3 ammoniums. We have 6 over here on the product side, so you ask yourself, 3 times what is going to equal 6? The answer is 2. So I'm going to go ahead and write 2 over here. This becomes 6. That 2 is also going to impact our phosphate. We had 1 initially, but now we have 2 times 1, which equals to 2. And it seems like we're done. We have 3, 3, 6, 6, 6, 6, and 2, and 2. All good? Alright guys, so we have done a lot of these examples. So what I did is just write the final answer here for the second one. So you can go ahead and pause the video to make sure that you got it correct. The next question is telling us to consider this chemical equation, and then they say, how many moles of dioxygen are needed to react with 6 moles of sodium? So every time I'm starting a question like this, I like to write where I'm starting and where I'm going to, so that I have some type of perspective when I'm solving the problem. So I'm starting out with 6 moles of sodium, and they're asking me for moles of dioxygen. So notice how you're starting with sodium and you're finishing up with dioxygen. So you start with one reactant, finishing up with another reactant. Every time that that happens, you have to use the mole ratio. So every time that you started with one thing and finishing up with something different, you have to go through the mole ratio. So let's go ahead and do that then. We're right here and we have to go through the mole ratio to get our answer. So we're starting out with 6.0 moles of sodium, and I said we're going to be using the mole ratio, so moles and moles. What I want to get rid of is going to go at the bottom of the fraction, so I want to get rid of the moles of sodium. That's going to go down here, and I want to end up with the moles of dioxygen. So that goes on the top. The numbers that are going to be going in here will be the coefficients after the reaction is balanced. So this reaction is balanced already, and I'm going to look at dioxygen, whatever coefficient it is. So this one is 1. And for sodium, the coefficient is 4. Now you're going to go ahead and plug this into your calculator, and your answer is going to be 1.5 moles of dioxygen. Let's go ahead and check the sig figs or significant figures. We have 2 over here starting out, and I'm finishing out with 2, so we're good. The next question is asking, how many grams of dioxygen are needed to react with 16.5 grams of sodium? So again, first of all, I want to go ahead and know exactly where I'm starting and finishing up. So I'm starting with 16.5 grams of Na, so sodium, and I want to end up with grams of O2. So again, I'm starting out with 1, finishing out with a different one. I'm going to have to use the mole ratio at some point. But we're over here, and we have to go from grams to mole ratio to finishing up with grams again. So let's go ahead and do it. We are starting out with 16.5 grams of Na. My next step is to get moles. So I'm going to be using the molar mass. Whatever I want is going on the top. So I want moles. I want to get rid of grams. That goes at the bottom. And then you're going to be using the molar mass. So that's going to be 22.99. You're going to plug this into your calculator. And the answer is going to be 0.717703 moles of Na. Now I'm going to take this number and we're going to go through the mole ratio. So I've written the moles of sodium over here. And again, we're right here and we're trying to go to the mole ratio. So let's do that. We're trying to get rid of moles of sodium. So that's going to be going at the bottom. And I want to end up with moles of dioxygen. So that's going to be going on the top. The numbers that go here will be the coefficients after the reaction is balanced, which, like we said, is already balanced. So we have dioxygen with 1 and sodium with 4. So you're going to plug this into your calculator and your answer is going to be 0.179426 moles of dioxygen because the moles of sodium have crossed out. Now I'm going to take this number right here, the moles of dioxygen, we're right here, and I'm going to go to grams. So in order to go from moles to grams, again, I'm going to be using the molar mass. So I wrote over here the moles of dioxygen, and like we said, we're going to be using the molar mass to get rid of the moles. So I want to get rid of the moles, it's going to be going at the bottom of the fraction. Whatever I want, it goes on the top, and I want grams. And the molar mass of dioxygen is going to be 32.00. You're going to plug this into your calculator, and the answer comes out to be 5.74163 grams of dioxygen. Now let's not forget about the significant figures. We started out with 3, so our final answer should also have 3. So I'm going to stop right here, right? 1, 2, 3. Evaluate this number to see whether or not you need to round. The answer is no. So this right here is going to be my final answer. 5.74 grams of dioxygen. This question is now asking, how many grams of sodium are needed to produce 11.5 grams of sodium oxide? So again, the very first thing that we're going to be doing is writing our starting point and where we need to finish up. So we're starting out with 11.5 grams of sodium oxide, and our goal is to end up with grams of sodium. So looking at our chart, we're starting with grams. We have to go to moles, use the molar ratio because again, we're starting out with the product and we're going to be finishing up with one of the reactants. So because I'm starting and finishing up with something different, I have to go through the mole ratio. So I'm right here, then to moles, then to mole ratio, and then you're gonna be getting the grams. So let's get started. We have 11.5 grams of Na2O. My next step is to go to moles. So whatever I want is going to go going on the top, and what I want to cross out is going to go at the bottom, and I'm going to be using the molar mass. So the molar mass for sodium oxide is going to be 61.98. This is going to allow for my grams to get crossed out, and now the moles are going to be 0.185544. And now I have moles of Na2O. Now I'm going to be writing this over there. So I did it. I wrote over here the moles of sodium oxide, and now I'm here and I have to go through the mole ratio to get to the grams. So let's do that. What I want to get rid of, which is moles of sodium oxide, is going to go at the bottom, and what I want, which is moles of sodium, is going to go at the top. And over here, you're going to be writing the coefficients after the reaction is balanced, like we've mentioned before. So the coefficient is going to be 2 for sodium oxide, and for sodium is going to be 4. So you're going to be plugging this into your calculator, and the answer is going to be 0.371087. Notice how we've crossed out moles of sodium dioxide, and now we have moles of Na. Now I'm going to be taking these moles of sodium, and I'm going to be using the molar mass to get to grams. So I wrote the moles of sodium over here, and let's use now the molar mass to get to grams. So what I want goes on the top, what I want to get rid of goes at the bottom, and I'm going to be using the molar mass of sodium, which is 22.99. You're going to be plugging this into your calculator, and the answer is going to be 8.5313 grams of Na. Notice how you've crossed out moles of sodium, and now you are left over with grams of sodium. Let's not forget about significant figures. We had 3, so our answer should also have 3. So we have 1, 2, 3. Stop right there. See if you have to round. The answer is no. So my final answer then is this: 8.53 grams of sodium. Now we have this question right here asking us to consider this chemical equation, and then it says, what is the theoretical yield if you have this amount of reactant number 1 and this amount of reactant number 2? So first of all, what is a theoretical yield? The theoretical yield will be how much product you could possibly recover if we lived in an ideal world. So if there were no experimental errors, if the reaction went to completion, right? But we don't live in an ideal world. Regardless, they want to know what is the theoretical yield, and in order for us to know what the theoretical yield is, we need to know which of these two reactants is going to be the limiting reactant. The limiting reactant will be the reactant that runs out first and therefore limits the reaction. So in order for us to do that, we're going to analyze which of these two reactants is going to be producing the least amount of moles of our product. So let's go ahead and do that. I'm starting out with 30.0 grams, reactant number 1, and 65.0 grams of reactant number 2, which is here 2. And like I said, I'm starting with grams of one reactant, and I'm trying to figure out how many moles of the product that reactant is going to be able to produce. So in other words, I'm going from grams of this reactant to moles of this product, and then same thing, grams of this reactant to moles of the product. We're starting out with one and we're finishing out with another one. What are we going to have to use at some point? The mole ratio, okay? So we're right here, grams, we need to go to moles. So let's do that. Whatever you want is going to go at the top. Whatever you need to get rid of, grams, is going to go at the bottom. You're going to be using the molar mass, which is going to be 78.11. And you're going to plug this into your calculator. It's going to give you 0.38407 moles of reactant number 1. Okay. Then you're gonna go ahead and get this and do the same thing. Go to moles. So I want moles. I want to get rid of grams. And the molar mass is going to be 159.81. You're going to plug this into your calculator. And the answer is going to be 0.406733 moles of the R2. So you can now go ahead and stop right here because, again, we're trying to figure out which of these two is going to generate the least amount of moles of product, okay? So here we have moles of reactant 1, moles of reactant 2, and you can now go ahead and compare two things that are different, right? You have one molecule here and another molecule here. You cannot determine, based on the moles that we have right now, which of these two is going to be able to give you the least amount of moles of the product. So what we will have to do is use the mole ratio to get rid of this reactant and come out with a product, and same thing, use the mole ratio to get rid of this reactant and come out with the product. So let's go ahead and do that. So I've written the moles of each reactant here, and now we're going to be using the mole ratio to figure out how many moles of the product will be produced by each one of these reactants. So let's go ahead and do that. Right, we were there, we're trying to go through here. So I want to get moles of the product, and I want to get rid of moles of this reactant. And the number that will go here will be of the coefficients of a balanced reaction. So that's why it's so important that you have to make sure that this is balanced before you even start, okay? So this will be 1, this will be 1, and the answer, because it's 1 to 1, will be the same. Had it not been 1 to 1, we have a situation going on, right? That's why it's important, like I said, to make sure that it is balanced. 0.7 of our product. Now, same thing. We are doing the mole ratio again. The moles of what I want go on the top. So, of our product, what I want to cross out, moles of our reactant. Number 2 is going to be going at the bottom. And over here, same thing, the coefficients after the reaction is balanced. So this one is 1 to 1 as well. So the answer will be the same. 0.406733 moles of our product. So now that we have the same molecule here and here, we can go ahead and compare these two answers, right? And based on this, you know that there is less moles of this than moles of this, right? They're the same thing, but reactant number 1 is going to be producing the least amount of moles of the product, which was what we were interested in, right? We were trying to figure out which of these two reactants was the limiting reactant, meaning which of these two reactants is going to be running out first and therefore generate the least amount of moles of the product. So because we figure out that we have less amount of moles of the product here, then that means that reactant number 1 is going to be our limiting reactant. So since we figured out that this reactant was going to be our limiting reactant and that this reactant would generate this amount of moles of product, then I can take these moles of product right here and I can figure out the grams of the product that will be produced. Therefore, my theoretical yield. So I'm going to go to grams and therefore use the molar mass of the product. So I want to get rid of moles. That's going to go at the bottom. I want to end up with grams. That goes at the top. And you're going to be using the molar mass, of course. So it's going to be 157.01. You're going to be plugging this into your calculator. And the answer is going to be 60.3 grams of the product. Alright, then let's check the significant figures. We have of our limiting reactant, 1, 2, 3 significant figures, and we ended up with 3 significant figures. So we're good. Now that we found the theoretical yield, they're asking us, if the actual yield of the product was 56.7 grams, what is the percent yield? So the percent yield equation is going to be this right here. Is the actual, which is what they're giving us right now, over the theoretical, which is what we found in the previous question, times 100%. So what they're pretty much telling you is that, hey, you went to the lab, you did this experiment, and what you got was this. This is your actual value because it's the one that you got experimentally, right? You go into the lab, you lost some product, maybe the reaction didn't go to completion, whatever might have happened, this is what you actually got, okay? You lost some product. Now, you're going to take this value, you're going to plug it in. The theoretical is, like I said before, if we live in an ideal world, we would have gotten 100% of our product. That's not the case. So we're going to be putting the theoretical in here, times 100%, that's going to give us the percent yield. So let's just do that. The actual is 56.7 grams. The theoretical, which we found earlier, was 60.3 grams. You're going to take that ratio, multiply it by 100%. This equals to 94.0291%. Now let's go ahead and check for significant figures. We were given 3 sig figs, so we have 3 versus 3. Our final answer should also have 3, so we have 1, 2. Stop right there. Do we have to round? The answer is no. So our final answer is 94.0%. If you made it this far, thank you so much for watching and for paying attention. If you have any questions, leave me one in the comment section or go ahead and send me an email. Other than that, thank you so much for watching and I will see you in the next video.